Hello, welcome back to Statistics and Mathematics YouTube channel. Today we are going to discuss what is termed as geometric distribution. Geometric distribution is a series of independent Bernoulli trials with constant probability P of success. Okay? Yes. So what that we are trying to say is that the geometric distribution, right, observe the number of trials of an experiment until the first target is being achieved, right? So these are some of the examples of geometric random variable, and they are said the number of pregnancies required before the first boy child is being born. Let's say a female girl may give birth to a series of children. For instance, maybe he has given birth to 5 children, of which all of them are girls. Okay, if he give birth to a second child, of which that child is a boy, that is the first success of that female girl being given birth to a boy. And this example is a geometric random variable. And then the second one is saying that the number of oil well needed to be drilled until the first successful oil well is hit. It means that you are going to drill the wall until you hit an oil wall. Okay, that is an example too of a geometric random variable. And then the last on the list is the number of shots fired before the first target was hit. Okay, so here you are going to fire the shots series of time until you hit your first target. And these are all examples of geometric random variables. Since you have understood the introduction of this geometric distribution, let's dive into how we can get our PMF. And this PMF for geometric distribution, they are into two folds. Okay, so they are into two folds, and the first one is in a series of independent Bernoulli trials with a constant probability P of success, let the random variable x denote the number of trials until the first success. So here, if our random variable x denote the number of trials until the first success, then our PMF for the geometric distribution will be equal to P times 1 minus P all raised to the power x minus 1, where our x will be 1, 2, 3 up to infinity. Right? This PMF holds if our x denote the number of trials until the first success. And for the definition 2, we are saying that in a series of independent Bernoulli trials with a constant probability P of success, let a random variable x denote the number of failures before the first success. Right? If our x, which is the random variable, denote the number of failures before the first success, then our PMF will be P times 1 minus P all raised to the power x. So here it will not be x minus 1, but rather x. Okay, yes, that is the 2 PMF for the geometric distribution. Okay, yes. So sometimes you may be asked to also calculate for the mean, variance, moment generating function, the characteristics function of the geometric distribution. Right? This one holds for the number of trials until the first success. So here the expectation of x will be equal to 1 divided by P. Okay, this will be our expectation. And our variance will be equal to 1 minus P divided by P squared. And then the moment generating function will be equal to P e raised to the power t divided by 1 minus Q e raised to the power t. Okay, where our t is less than negative length of Q. Okay, so here this is the moment generating function. And then if you want to get your characteristics function, anywhere you see the t, add I to it. Okay, yes. So here, once you add I to this, you have gotten a characteristics function, which will be given as P e raised to the power it divided by 1 minus Q times e raised to the power it. And this is what our characteristics functions. There are some theorems here that I want us to also discuss. But before we go to that theorems, I want us to also get the mean, variance, moment generating function and characteristics function of the geometric distribution when we have the number of failures before the first success. Okay, yeah. So here that one will be the expectation will be 1 over P minus 1, of which here we are going to get 1 minus P divided by P. That will be our expectation. And our variance will be 1 minus P divided by P squared. And then our moment generating function here will give us P divided by 1 minus Q e raised to the power t. This will be our moment generating function. And then all that we are going to do for characteristic function is to just replace the t here with it, of which we have it here, and then that is our characteristic function. Now I want us to discuss some theorems. Okay, they are saying that let x have a geometric distribution with probability mass function, this, which is equal to p times 1 minus p raised to the power x minus 1. Okay, yes. So we are saying that if you have this one and then we are having probability that our x is greater than x, right? We are asked to calculate probability that our x is greater than x is equal to what? Probability of what? Failures, which is raised to the power of 1 x, where our q is equal to 1 minus p, right? So let's prove this theorem. Okay, yes. And then we know that probability that our x is greater than x is equal to probability that our x is equal to s plus 1 plus probability that our x is greater than, our x is equal to s plus 2 plus our x is equal to s plus 3 up to infinity. Okay, so if you want to we can write this one in this form. Okay, so first we are going to use the number of trials until we get our first success, which will give us probability of x, which we are going to get p times 1 minus p all raised to the power x minus 1. Okay, so for this one, probability that our x is equal to s plus 1, we are going to get p times what? 1 minus p all raised to the power x plus 1 minus 1, of which you are going to get this one. So this one is going to cancel that. You are going to get this one. And then probability of success times 1 minus p all raised to the power x plus 2 minus 1, of which you are going to get p1 minus p all raised to the power x plus 1. Okay, of which you are going to get this one. You are going to get this one. We are going to get this one if you follow the trend. Okay, so you see we have something in common here that we can factorize out, and we have what we have in common is what? P times q raised to the power x. We can factorize it out of this sequence, and then we are going to get p times q raised to the power x bracket open 1 plus q squared plus up to infinity. Okay, yes. And then for this one, this is what? A geometric one sequence, of which for geometric sequence 2 we can calculate it in this form: 1 divided by 1 minus 1 r. Okay, of which this r is what? Our common difference. Okay, so once we have this one here, we can use geometric sequence to get this form. Okay, so this one will give us pq raised to the power x bracket open 1 divided by 1 minus r, and then 1 minus r, our r2 is equal to q divided by what? Q squared divided by q, which will give us what? Q. That's the common difference minus what? Q. So that is what we have here. Okay, and the 1 minus q2 is what? P. Okay, so this one is going to multiply to, you are going to get p raised to p times q raised to the power x divided by 1 minus q, which is p, and this p can cancel that, and we are going to get our final answer to be q raised to the power x. So that's the reason why I'm saying that if we have probability that our x is greater than x is equal to what? This one. Okay, yes. And then that is the same thing for the number of failures until we get our first success. We can prove that one too, and then get this one. Okay, so let's go to one of the biggest properties and the popular property of a geometric distribution. That is what? The lack of memory is what? Property. So the lack of memory property states that if x has geometric distribution, then our probability that our x is greater than s plus t, given s is greater than x, is equal to probability that our x is greater than t. So let's prove that one. How can we get this one? Let's prove it. So probability that our x is greater than s plus t, given our x is greater than x, is what? Probability, that's a joint. Okay, that will give us probability that our x is greater than s plus t, comma s is greater than x, all divided by probability that our x is greater than x. Okay, this is what we are going to have. And then you see we have to get the intersection of this one. Okay, you have to get the intersection of x is greater than s plus t and then x is greater than x. Okay, the intersection of this one will give us what? Probability that our x is greater than x plus what? T, all divided by probability that our x is greater than what? X. And then we also just learned that probability that our x is greater than x is equal to q raised to the power x. So here this one too is equal to q raised to the power x plus t, since this will be what? Our exponent. Okay, and then divided by q raised to the power x, which will be this. So we could see clearly that this one can be q raised to the power s times q raised to the power t, all divided by q raised to the power s. This will cancel that, and we will get our final answer to be q raised to the power t. Okay, yes, that is our answer as we can see here. So that is what the memoryless property that we have in geometric distribution. Okay, so our next video we are going to solve more examples on the geometric distribution. This is Statistics and Mathematics YouTube channel. If you haven't subscribed, kindly subscribe, like and share so that this video will get to your friends for them to also watch. Bye, have a lovely day.